Gluconeogenesis is going to be the generation of new glucose. And when you break down the word, that is literally what it means. So genesis for generation, neo for new, and that gluco for glucose. And this is going to use common metabolites, especially things like pyruvate. So the synthesis of glucose from small molecule precursors. This is going to be a really nice example of showing the anabolic pathway that is going in the exact reverse direction of the catabolic pathway. So we just talked about glycolysis, and now we're into gluconeogenesis. This is going to show again how these things can be regulated so you only actually have one of these active at a time and only active when they're required. The main thing to remember here is that your anabolic pathway is not just the reverse. So while there were 10 steps in glycolysis, we're going to see that a lot of those enzymes are still used by gluconeogenesis, but not all of them. So it's not just a reverse of all of those pathways. The human body does actually need glucose. So we were talking about glycolysis, it seemed like, oh, well, we need energy. And so glucose is just a nice way to get energy. But the brain also uses glucose specifically. So the body does carry a certain amount of glucose, and about 200 grams available as glycogen. Those glycogen stores are going to be depleted, at least partially, by strenuous exercise. And so the body's got about a day's worth of glucose. So if we don't get enough new from our diet, then we're going to have to create glucose. We're going to have to make and synthesize glucose in our bodies, which we can do. The important thing here is that fat catabolism does not generate glucose. So whenever you break down fat, you do not get sugar out as a result of breaking down fat. The pyruvate and lactate that are produced during exercise can be recycled to glucose. So as our body breaks down glucose by glycolysis, it can go ahead and use those products of either pyruvate and lactate and use those then as substrates for gluconeogenesis. This is going to occur mainly in the liver and the kidneys. And the main thing to remember again is this is not just a simple reversal of glycolysis. The glycolysis has a negative delta G value, we're looking at all those concentrations, products, and reactants, about negative 74 kilojoules per mole. So glycolysis is favorable. Glycolysis will move forward. So the hard thing here is that if gluconeogenesis was just the reverse, then the delta G value for gluconeogenesis would be positive, and there wouldn't be any driving force to have gluconeogenesis move forward. So there has to be something changed to have the energetics be favorable for our anabolic pathway. The other thing that's going to happen with this is there's got to be reciprocal regulation. So reciprocal here because it's going to affect not just gluconeogenesis, but also glycolysis. So we need regulation that's going to be able to activate glycolysis and turn gluconeogenesis off, or do the opposite where we've got regulation that can make sure that gluconeogenesis is running and is proceeding, but is turning off glycolysis. So again, gluconeogenesis is not the simple reversal of glycolysis. There are a variety of intermediates that can be used. We talked about pyruvate, lactate, a lot of amino acids, glycerol, and citric acid cycle intermediates can all be converted to glucose by gluconeogenesis. So the body's got a lot of different precursors that it can use. Both brain and muscle are going to be the major sites of that glucose consumption. But your liver and your kidney is going to account for almost all of the gluconeogenesis. So your brain and your muscle is what needs that fuel, but the brain and your muscles are not the ones that are going to be producing it. So in the human body, we're going to need that bloodstream to actually carry and transport the glucose from liver and kidneys to the brain and muscles. It is going to appear to be the reversal of glycolysis, so we'll see some diagrams in a minute that will show something fairly similar. Which realize that you are making glucose, so gluconeogenesis will give glucose as an ultimate product, and it will go ahead and consume ATP and NADH. But again, it can't just be a reversal because glycolysis is going to be exergonic. So glycolysis usually releases energy and has that forward motion. So we're going to need different enzymes to allow regulation of the two pathways. So taking a closer look at the pathways. So what you see here is that on the left is glycolysis. So this is where we would start with glucose and we would move down to pyruvate, potentially keep going to lactate. and gluconeogenesis then on the right. And what you'll notice is that most of the substrates are the same. Most of the enzymes are the same, but those highlighted in yellow are different. So 7 of the reactions from glycolysis are shared. So reaction 2 and reaction 4 through 9. So a lot of them are shared. But there were 3 steps in glycolysis that were highly exergonic, and those are the ones that we have to replace. However, in replacing those 3 steps of glycolysis, we're actually going to have 4 enzymes. So gluconeogenesis, we're essentially going to start with pyruvate, which is down at the bottom. And in order to replace the 1 enzyme of pyruvate kinase that we have in glycolysis, we're actually going to have 2 different enzymes. So pyruvate carboxylase and phosphoenolpyruvate carboxykinase are going to work together to replace the 1 reaction of pyruvate kinase. So that's where you're going to see that it's going to take 2 different enzymes to replace the 1 in gluconeogenesis to go in this anabolic pathway. Then, as I'm sure you expected, we spent some time talking about phosphofructokinase in glycolysis, and we're going to have a different enzyme, fructose 1,6-bisphosphatase, to replace phosphofructokinase in that reaction. So we have a separate one there. And lastly, replacing hexokinase from glycolysis is going to be glucose 6-phosphatase. Something that you might notice in that terminology is that phosphofructokinase was where we were taking a phosphate group and putting it onto a substrate. Hexokinase, we again were taking a phosphate group off of ATP and putting it onto a substrate. And now we are needing to take those phosphate groups off. And so as we're removing those phosphates, now we actually see phosphatase reactions. So you can actually still pay attention to some of those terminologies, those enzyme names to tell you what's going on. So again, you've got a couple of different enzymes. And we are going to spend more time and more detail on all of these. So just again, that pyruvate carboxylase is going to convert the pyruvate to oxaloacetate, and then we're going to have PEP carboxykinase making phosphoenolpyruvate from oxaloacetate. So again, it's going to take 2 different enzymes and essentially 2 steps to get the gluconeogenesis pathway going. And again, here to replace phosphofructokinase from glycolysis, we're going to have fructose 1,6-bisphosphatase. That is going to be what's going to dephosphorylate fructose 1,6-bisphosphate to fructose 6-phosphate. And then again, finally, in gluconeogenesis, the last enzymatic reaction is going to be glucose 6-phosphate being dephosphorylated to glucose by glucose 6-phosphatase. So gluconeogenesis, again, is going to retain 7 steps of glycolysis. So a lot of things are still there that are the same from glycolysis. And again, there's going to be 4 different enzymes that are replacing 3 steps in gluconeogenesis. Those replacements are going to allow us to have a spontaneous pathway. So gluconeogenesis will also have a negative delta G value in the direction of sugar synthesis. So this anabolic pathway will still be able to proceed forward. So this is just to remind you when we're looking at glycolysis that you again have those sets where you have those negative delta G values, and those are the steps where we see regulation occur, and those are the steps that now that we're looking at gluconeogenesis, those are the steps that are being targeted to have replacement enzymes. So those steps in the glycolysis cycle of hexokinase, phosphofructokinase, and pyruvate kinase, those are the ones that we're looking at replacing and getting a new set of enzymes in gluconeogenesis. The substrates for gluconeogenesis are going to be things like pyruvate, lactate, and amino acids. The big thing here is that fatty acids cannot be utilized. So most of those fatty acids will only yield acetyl-CoA, and acetyl-CoA can't actually provide for net synthesis of sugar. They need something else to go along with it. So when we're looking at this pathway, again, there are a lot of different parts of biochemical pathways that can provide and feed into gluconeogenesis, but fatty acids cannot do that. So we're going to be looking mainly for things like pyruvate, lactate, and amino acids.